Awesome. You can actually see the. The problem is right now we actually don't have the stream in advance of the actual lecture, so no one would actually know like this is going to that site. They will hopefully if you guys know what's going on by next week. So it'll be like one of you will take charge of, yeah, send us the link for the thing that you prepared, and then if someone misses, they could watch it from home or from the front desk of New College, for example.
But you'll see, it's very clear like which link is which. There's a little box that you'll see. Yeah. Also, we're both in the Facebook group, so
Just basically plug everything in so the presentation
everything's plugged in. Open up all the windows. Also, I really class, so if something goes wrong,
All right. Thanks for your help, guys. We'll hope for the best. All right. All right. All right. Thanks for your patience, everyone. I think we're all set, ready to go. Wait, how do I advance the slide, Jeffrey, Michael? I can't actually advance the slide, I don't think. Do I go to a different tab? Okay, let me. Okay, got it. I figured it out. Sorry to bring you back down. All right. Okay, so I think. Oh yeah, there's one over there. So I think if we don't have anything else to kind of talk about, the first thing I wanted to really encourage you to do is to make sure that you're signed up for a tutorial. So the tutorial this week will start off kind of a little bit slow. We will actually have the tutorials covering the same lecture topics, giving you some insight into what to expect for the upcoming term tests. And it's really to get you prepared for either the term tests, the final exams, or the assignments, and how to do well on any or all of the different things that you're going to have to encounter throughout this course. So if you haven't signed up, please do so. The tutorials do start this Thursday. It's a good way to kind of make sure that you understand how to get 10 out of 10 for your participation. I do strongly encourage you to talk to your TAs. They're the ones that are going to be evaluating you for a large proportion of your marks, and they're going to be also grading and evaluating your term tests and potentially your final exam as well. So it's an awesome opportunity for you to get to know the different people in your class, as well as your TAs and what they do for research, et cetera. So I'm going to do a quick recap from the last class, and we'll get going on a couple of slides that I didn't finish from the last class, where we're starting to learn a little bit about metabolic syndrome, also called insulin resistance. And they're not identical. Insulin resistance is one part of metabolic syndrome, but I kind of use those interchangeably, and I'll go back over that and a couple of questions that came up in the last lecture as well. And then we're going to do a couple of side detours that are related to the topics that we're going to be covering here today. And then we'll start into the process of understanding these different animal models. And you'll see some molecules that you're going to have to remember for when we start talking about skin and skin cancer a little bit later on as well. And the big take home from today is that when we start looking at measures of central obesity, and that's one of the hallmark features of metabolic syndrome, and it's not equal and it's not the same in different populations. So for example, the South Asian, East Asian populations, some of the measurements that were done may not be reflective of like having central obesity. And so we're going to talk about that. How do we understand if someone is at risk for metabolic syndrome when they don't have a waist ratio or waist to hip ratio that is not reflective of the numbers that the World Health Organization uses. So a lot of the lecture will kind of revolve around that. So some of the questions that came up from the emails that I received and that were also there for the discussion board, some of you were asking, are all of these different measurements, like the triglycerides, the fasting glucose levels, and then the HDL, is that also in milligrams per deciliter? And yes, the answer is yes. All of these are in milligrams per deciliter, and these are, again, pretty standardized lab values. So if you go in and you ask your family doctor for a full blood workup, you'll actually get these numbers and the appropriate ranges that you should expect to see for health. And we talked about the medical evaluations and the physical evaluations in the last lecture. So some things that you can measure like waist circumference, the body mass index, those are useful indicators, but they're probably not great indicators. And these medical evaluations are a little bit more specific, and they too have some issues, but we'll talk a little bit more about them before we finish this lecture series. I then went into talking a little bit about insulin resistance, and this is type 2 diabetes. Insulin resistance is one of the features of metabolic syndrome, and this is where we start with like having insulin release. And insulin release is important, as we talked about in the last lecture, because without insulin, your cells, your muscle cells, your fat cells, your liver cells can't really take up the glucose that they're encountering in the blood. So the glucose levels stay high in the blood, and actually that's incredibly bad for you. The higher your blood glucose levels are, and the longer that they remain high, your immune system is being affected. And so if you have a tiny little cut, and you're diabetic and you have hyperglycemia, that wound, that cut, actually takes a long time to heal, much, much longer, and we'll cover this in the next lecture, and the immune system and how it gets affected by hyperglycemia. It takes much, much longer for wounds to heal in diabetic individuals, whether it's type 1 or type 2. That means that they're more likely to have infections, and in addition to that, the nerves start to become desensitized. And so we know high glucose is not something that we want. Your normal body response is to lower that to euglycemic levels as quickly as possible. And in type 2 diabetes, it releases insulin, but the cells just are not responsive anymore. There is no translocation or the movement up to the cell surface. So this translocation that you see here from the inside translocating up to the cell surface, without this translocation of a glucose transporter, glucose can't really enter into the cell effectively. Okay? So we were talking about that and the importance of that in the last lecture as well. And so a lot of the things that we're going to be talking about is this platform around the hyperglycemia, the insulin non-responsiveness, and we're going to be using diabetes as one of the different integrative modules that allow us to study the physiological aspects of a number of different systems. So I didn't really talk about this slide, and this is where we're going to pick up from today's lecture. So one of the things that you know happens is that in response to high levels of glucose, or after eating, after this food intake, then one of the things that we might expect to see is that we get this release of insulin. And in fact, one of the things that we do see is that different tissues, including like muscle tissue, actually are no longer responsive to insulin. Insulin is there, and it's trying to get the glucose transporter to get up to the cell surface. It's trying to deposit some of that glucose into muscle tissue, into adipose tissue, etc., but it just is not very effective. And so we get this hyperglycemia to begin with, but over time, we actually start to release more and more insulin. And so we get hyperinsulinemia as a result of this lack of insulin responsiveness. Okay, and some of the other features that are on this slide I'll come back to and talk to you about later. But here, really the key concept is that in insulin resistance or type 2 diabetes, and this is all a subsection of metabolic syndrome, we have both high blood glucose, hyperglycemia, and in addition to that, we also have hyperinsulinemia. We have too much insulin. It's just not responsive. And that's really the major point of this slide. I'm going to integrate all of these, the adipose tissue, the macrophages, why they're kind of put together, as well as what happens to the inflammatory response that you see here that accompanies this hyperinsulinemia and the hyperglycemia. Another aspect of metabolic syndrome is that you have an inflammatory response. It's like your body is infected with bacteria, but there is no infection. And your body has these high levels of cytokines because we have high glucose and we have high insulin levels. And that's, again, the primary purpose of this slide and what you're responsible for. So again, just a little check-in. Is there anything that you need me to confirm or anything that you're not sure of in terms of what you need to know on this slide, or just any general questions? No? Yes, no, maybe? Complete silence. Okay, awesome. Or not awesome, but we'll hopefully get over the lack of responsiveness in a little bit. So a couple of things to mention here, and this goes back to the physical exam. So we can physically measure the waist circumference, or another measure that's, again, to tell you the difference between where it's being deposited. Is it above the waistline or below the waistline? So in addition to the waist circumference, we can also measure the hip circumference. So either the waist to hip ratio or just the waist circumference. And we will get some sort of body type, whether it's a pear shape, apple shape, gynoid, android type body shape, which, by the way, if you don't recall that at all, do you guys remember android, gynoid from last week? Do you remember the different, how many classes were there as I put up my, yeah, right, okay, great. Good job, Bill. Give the answer ahead of time. So 4 different classes. Do you expect to see that on your first term test? A lot of really good shaking heads here. So it's a good idea to go back and review that. And you'll hear a little bit about what to expect in terms of a potential question around that and what to think about from your tutorials this week on Thursday. So one of the things that I was kind of mentioning is that we get different types of fat deposition. So we can get things under the skin, which we call subcutaneous deposition, and then we get intra-abdominal or visceral fat deposition. And the weird thing is, and what I really want you to take away, is that where you deposit that fat or the adipose tissue is actually important because they have different features. Okay, and I know it sounds like it's a different concept, but in fact, it's actually a pretty simple concept if you think about it. So the fat that you have deposited inside your abdominal cavity might be adipocytes, but they have very, very different physical properties. They look different, they secrete different things than the fat deposition you have under your skin, that subcutaneous fat. And again, I'm not the best example of this, but the hair on your head, for example, is a little bit different than the hair that you have on your arms, and that's sort of the difference, right? It's still your hair, it's your genotype, but they have very different properties, they will grow differently, and it's the same thing with the different types of adipocytes that we have intra-abdominally versus the ones that are found subcutaneously. And so we were talking a little bit about some of the issues that we find with this. So the hyperinsulinemia, the hyperglycemia, and then we have 2 different types of fat deposition, and these adipocytes that we find either intra-abdominally, inside your visceral cavity, or under your skin are completely different. So we have very different types of fat tissue. The adipose tissue are completely different, and that again is the focus of what we'll be talking about. The other thing to make note of, do you think everyone has the potential to develop metabolic syndrome? So it's like every last one of you here, and it's an important question. Is everyone here susceptible to developing metabolic syndrome or type 2 diabetes? Yes, no? How many of you say yes? Blink hard now. You don't have to raise your hand. How many of you say no? You can do a double blink now. Can't tell. Okay. All right. So we think that type 2 diabetes is polygenic. It's almost 100% guaranteed that it's polygenic. Multiple genes are involved in the pathogenesis of type 2 diabetes, and even for some of type 1 diabetes that I'll get to later. And so it's hard to really determine if you had the genetic background to develop metabolic syndrome. But there do seem to be some individuals that will not develop metabolic syndrome, and they may not carry all of the genes necessary for developing type 2 diabetes or metabolic syndrome. So it's, again, a really interesting area of research. So this is something that we didn't talk about in the last class. All of you have heard of magnetic resonance imaging, MRI, right? Have any of you had an MRI done at some point? Not of your brain, but maybe of your knee or a muscle system or your brain. Have any of you had an MRI done? So a lot of you have had that done. In fact, Amanda is an expert in MRI, if I'm not mistaken, right? Yes, okay, awesome. And you can ask her a little bit about her research if you're in her tutorial as well. And I wanted to just mention a couple of things. Because we're not sure of whether or not these measures, so like the waist circumference may not be great, BMI is not a great measure of determining whether or not you're at risk for metabolic syndrome or central obesity. And so MRI is potentially one of those different diagnostic procedures that I didn't talk about in the last lecture that actually allows you to determine where that fat or the adipose tissue is being deposited. And what you're seeing are two different individuals on this diagram. So you're seeing an individual here at the top. So these are MRIs of the same individual. And again, without going into like how MRIs are done, you can do what is known as a T1 weighted versus a T2 weighted image. And here, to look at fat, we can use a different type of MRI. So these are actually the same MRIs. They're just looking at different things. And you don't have to get scanned twice. It's just something that is done during the procedure itself. And everything that you see here in white represents intra-abdominal, centrally deposited adipose tissue, the not so good stuff, which I haven't told you why is not so good yet. And why am I bringing all of this up? So here is the outline of the person's waist. And in fact, these are the two pelvic bones that you see here. This is the spinal cord. And what you're seeing is the person is lying down. This is a cross-section. And this is sort of what their waist circumference would look like. Not very different from this individual down here. So these bottom two panels that you see here is a different individual. These top two panels that you see in the blue box, that's one individual, and these bottom two are a completely different individual. And so if you look, and if you were to just eyeball it, their overall waist circumference is really not very different. They look kind of similar. And even if you look at their total fat mass, which I'll talk about in a moment, they're kind of similar too, right? So would you agree, or am I just sort of spouting and I'm trying to sell you a story and it's actually not something that you really see? Do you see it or not see it? You don't see it. Oh, don't believe your prof. Yikes. Yikes. Okay. So do you see that the numbers are at least similar? 19.8, no tricks up my sleeve, nothing there. So the fat masses are pretty similar. But one of the things that you'll see is if we do the MRI for this individual here, and we're taking the same planes through the same area of the body, and we take a look at all of the white tissue that represents the intra-abdominal fat accumulation, even though their waist circumference is really not that different, and their fat mass, their total fat mass throughout their body is really not that different, you're going to see that the amount of this intra-abdominal or centrally deposited fat is quite different. In fact, if you look at the area, the visceral fat area, or the VFA, it turns out to be quite a bit different, 155 square centimeters versus 96 square centimeters. And this is one way, the numbers are not important, but this is one way that we can use a measure to see whether or not we have central accumulation, intra-abdominal accumulation of fat. And again, I've told you, and I'll go through why this particular type of deposition of adipose tissue is not healthy. Are we okay so far? Yes, you have a question, Omar.
Would an DEXA scan be prepared over an MRI, or do they provide the same level of accuracy?
So the question for those of you at the back, so which one is better? DEXA scans, which we'll kind of bring up again, or MRIs? What do you think? Or is there a difference? Okay, all right, yes.
I think with the DEXA scans from last week, we
Yep.
could also see more subcutaneous fat, but this one just seems to show more visceral fat.
Right, so this one is definitely concentrating on the visceral fat area, so that's 100% correct. DEXA scans are still, even though we have more of them, they're still not like widely dispersed through most hospitals. MRIs are like in every hospital, right? And there are, in some hospitals, there are multiple MRI machines. And so getting access to an MRI is a little bit more convenient for most individuals. So the ease of accessibility is probably better for MRIs. Any other questions that I can answer for you now? No. Okay. So MRIs are yet another way to measure for metabolic syndrome, at least for the central accumulation of this adipose tissue. So again, these are some of the ones that we looked at in the last lecture. So these are a combination of both medical diagnostic values versus just physical values that we measure as well. So waist circumference over 40 inches, triglyceride levels, HDL cholesterol, blood pressure. And if you have any three of these from this list, then that's a pretty good indicator that you might have metabolic syndrome. You might then go in and confirm that using like an MRI or a DEXA scan, etc. So these are the first steps to kind of say that you're not really all that healthy. There are a couple of other things to maybe look at as well. So let me again ask you this question. Do you think that you have to memorize all the values that are on this particular slide? Less confidence. Yes, no, maybe? Can I get a solid maybe? Solid maybe? Okay, so at least I got a solid maybe. So these are values that I'm not a huge fan of having students memorize numbers, but in this one instance, and in addition to the last lecture, I asked you to memorize one value for euglycemia. Did anyone remember that value? So 90 milligrams per deciliter, that's the normal glucose level. So if you can, it's probably a good idea because you'll get a short answer question where you have to supply some of these numbers to at least know at least three of these values from each of the men versus women on this particular slide. And it's a good idea to kind of be comfortable with it, all right? So I'm hoping that we've been talking about it several times, and it's one of those things that is actually important for you to make sure that you know. Anything that I can confirm for you before we go on, or anything that you want to stop and talk about? Anything else? No? It's a very quiet class. Are you guys all doing okay? No. Are you in like a glucose coma right now? Maybe. If you had the donuts, maybe not a good idea. Not sure. Maybe we'll skip the donuts next week. All right. So do any of you know this individual here? It's before your time. Well, it is before your time, but anyone? Anyone? Michael Jordan, right. Greatest of all time? Yes, thank you. Thank you, yes. All right, so he actually had like one of the lowest reported body fat indexes. So he had like very, very low, I think it was like 3 point something percent at one point in his college career. So 3.8% of his body mass was just fat. And for most average individuals, it's somewhere between 20 to 25% of your body mass is related to fat. So think back, without going back to your slides, do you remember those MRI values? Remember those MRI values? Do you remember if they were like above 20 or below 20? Remember, you didn't believe me that they were the same. It was 19.8, right? So they fall kind of in like the normal-ish range. So they wouldn't look like they had obesity or anything else. So again, that's sort of the normal range. 15%, like if you're an athlete, if you're like on a varsity team, 15% body fat is considered like outstanding, very good athletic level. And then if you're over 26% of your body mass, then you're considered to be in the obese. So it's a slightly different way to look at things related to fat indices versus like BMI as well. And in terms of how do they come up with numbers, how do you get these measurements? There are different ways in which these measurements can be taken. So measuring this adiposity, some of the easier ways, and I think, are any of you taking the HMB312 or 314 labs? 314 labs? So I think that if you're taking 314 labs, you're actually going to do some of these different measurements about your physical fitness, et cetera. So some of them involve like skin fold measurements. These are relatively cheap. They can be done in any general practitioner's office. There are about 3 to 7 standardized zones, so 3 to 7 different areas on your body where you actually measure. You have these little calipers put on your waist. You have ones that are put on your shoulder blade, et cetera, on the back of your arm. There are about 3 to 7 standardized zones. And there's some questions as to whether or not they're always accurate. They can give you a measure in these different areas of your body based on the caliper and how much pressure is being put on them as it's squeezing a different area of your body, what percentage of fat you have. There's a lot of questions. If you're not properly trained and you're not doing it right, your values can be very off. And so it's easy, it's cheap, but there's questions about its accuracy. Another way to do this is hydrodensitometry. It's very, very accurate. It's volume related. So you sit in a tank of water, you displace a certain amount of water, and based on some very basic physiological measurements, you can determine how much of your body mass is muscle versus fat, et cetera. This is much more expensive. It also requires a lot more expertise to be able to run this. So hydrodensitometry will give you those values like 15% to 20%, et cetera, but they're much more challenging. DEXA scans that we also talked about are rapid, can be done fully clothed. You don't have to worry about privacy issues. And you get these very interesting dual X-ray scans. And you can actually get good values related to adiposity levels at different parts of your body, not just around your waist, et cetera. And again, just keeping in mind, the old measurement was the BMI. These two individuals who have very, very different body shapes, their BMIs are actually identical. So this individual here on the left has a BMI of 31.7. Again, based on the criteria that we had last lecture, they would be considered to be obese. This BMI over here on the right is an individual who's a rugby player. They have a BMI of 31.7, different muscle mass, so they're heavier, but they're actually not considered to be obese. And so they actually have very different deposition of adipose tissue. So in terms of doing this, originally it was designed to measure bone density. So this is still the number one reason for why you get a bone density scan or a DEXA scan. They will use this. It's often used for osteoporosis, but as a side sort of product of this, they can also measure some of the different adipose deposition as well, and that's also been found to be very, very useful. So it tells you the difference between bone versus soft tissues, including body fat. And now this is a way that we can also get those values of like less than 15% or 20 to 25% or over by using this DEXA scanning. So the methods that we've learned so far for measuring adiposity are DEXA scanning, hydrodensitometry, We've also learned about using the caliper skin fold measurements. Some are more accurate, some are less accurate, some require special equipment, some don't. If you're wondering, does MRI give you a full sort of body fat content? It does not. It only tells you about central deposition. So it's not used to measure total body fat. Any questions so far or things that are not clear that I can clarify for you? Yes? They're primarily for men, so apologies on that. Good question. Anything else? Any questions? No? No? Okay. All right. So one of the things that I'm hoping that you're going to think a little bit about is why are we so concerned about this central deposition of this adipose tissue? And one of the things that I showed you on the earlier slide is that in metabolic syndrome, there is a link between having central deposition of adipose tissue. The adipocytes that are accumulating are actually producing low levels of cytokines continuously. They're not the same types of adipose tissue that you get here under your skin, the subcutaneous type. And so for those individuals that have metabolic syndrome and they have that central deposition, you will also likely find low levels of inflammation. They are not infected with anything. They shouldn't have an inflammatory response, and yet they always continuously have low-grade inflammation, also called meta-inflammation. And this is thought to involve like the dysregulation of these lipids. So we'll talk a little bit about potential mechanisms by which this might occur. It's not completely understood how these are all related, so I'll give you some theories about this either at the end of today's lecture or early on the next lecture. But there is a strong link between lipid dysregulation, having too much of these lipids in specific places and specific adipocytes, and this low-grade inflammatory response. Okay, so again, we'll talk about that in a second. So one of the things that is sort of the most interesting for us, and when we look at it in a human biology context, so how many of you have heard of different types of diets? Not doing them, but like just have heard of them. Different diets? Okay. Have any of you heard of the Paleolithic diet? Okay, so if you were to just give me like a 2-sentence, what is the Paleolithic diet? What is it? You've just heard of it, not sure. Yes?
I think it's a diet that consists of foods that are thought to have been available during the Paleolithic period, so nothing processed or...
Right, so no processed, a lot of nuts, berries, things that our earlier ancestors might have eaten. And again, you don't have to memorize anything on this, but our diets have really changed over the last, even the last 5 years it's changed. The last 50 years definitely has changed. And so there's a lot of worry about whether or not metabolic syndrome, because it is going up, and it's going up very, very consistently. And even though we think it's polygenic, more and more individuals are at risk of developing metabolic syndrome in 2020 than they were like back in the 2000s. So what's happened over the last 20 years? And more of the modern diet has changed like how available certain types of nutrients and amount of energy are, and where we're getting these different carbohydrates, etc. And again, you may or may not be aware of it. Just again, to put things in context, so if you were to go out and have a Tim Hortons hot chocolate, so I'm not sure if you're a fan of Tim Hortons or not, but if you go out and have a Tim Hortons hot chocolate, you pretty much have taken up your daily sugar content for the day. So that's it. You shouldn't be having any more sugar for the rest of the day. But obviously, we take in a lot of sugar throughout most of the day. So you might have like a can of Pepsi, or you might have something like a hot chocolate. And if you have more than one, then you've already exceeded your daily allowance for that particular day. So again, just for your own information, it's likely that we've really changed our eating habits over the last little while. these carbohydrates are much more easily available. And the reason why we think metabolic syndrome has been skyrocketing, so insulin resistance leading to cardiovascular and cardiometabolic diseases, is because of the readily available carbohydrates in our diet that we don't even realize, right? So how many of you would have thought that having like a small hot chocolate pretty much wipes you out for the day in terms of your sugar intake? I wouldn't have thought that in most cases. So again, some of the benefits of this Paleolithic diet. Overall, if you were to maintain a Paleolithic diet, and this is a slide you don't have to memorize. So this is a slide you don't have to memorize. It kind of outlines that for you. This slide, nothing for you to memorize. It's just to have a discussion of why metabolic syndrome is increasing. Paleolithic diet, much healthier in terms of lower blood pressure, more aerobically fit overall. And again, in terms of hunter-gatherers, there's a theory that their diets consisted of much more fiber. They were out expending a lot more energy. And so as a result of all of that, the obesity and diabetes was much more rare in hunter-gatherer societies. And it's thought that because they weren't able to access food, and it's just a theory, and there are some pieces of evidence to support this theory, and there's some pieces of evidence that don't support this theory. It's thought that we have metabolic syndrome because now, in the foods that we do eat, because we've come from hunter-gatherer societies, and every culture has come from hunter-gatherer societies, because it was really hard to find food, that when we did find food, we were selecting for genes that allowed us to take and store that food in the form of fat that we could burn off much more energetically, favorably to us later on. So we're using our own genetic backgrounds against ourselves, and so we're no longer hunter-gatherers, but we have the remnants of their genes, and as a result, if we have excess carbohydrates and we are storing them as fat, this is where we have those issues that we're going to be talking about today. So I think most of you have taken HMB322, the histopathology course, right? Yep. Okay, great. So again, just as a working definition for us, when we talk about adipose tissue, we'll use the same definition that I think all of you had, which is that this is loose connective tissue. And this consists of different cell types as this loose connective tissue, adipocytes that we're going to be talking about. And here is a large adipocyte, and this is full of triglycerides, as well as macrophages and blood vessels. You need to have all three to be able to consider this as a normal adipose tissue. There's one thing missing from this. Do any of you know? There's one other type of cell that we have to normally associate with adipose tissue. Yes? Fibroblasts. Not necessarily, no. It's a good guess, though. Anything else? Any other guesses? Other cell types. Your favorite cell type? What's your favorite cell type? Anything else? Any other favorite cell types? No favorite cells? None? Sorry? Plasma cell? Okay. Interesting favorite cell, but okay, not necessarily, but on the right path. So some of the lymphocytes, the T lymphocytes in particular, and the immune cells there are going to be important. So there is one thing missing, which are the different types of immune cells that I'll get to in a moment. So make sure you come back and understand that. And these adipocytes are sort of the major way in which we store these fatty acids and triglycerides. It's thought that we've developed genes that allow us to more efficiently store carbohydrates as fatty acids when we were hunter-gatherers. And we tended to store those in the central abdominal cavity for readily accessible release of this stored energy back when finding food was really, really hard. So many of us have the remnants of those genes, and again, this is why it's probably polygenic. So we need some of this adipose tissue. It's important for cushioning tissues, as well as just for insulation in general. Okay, so again, this hunter-gatherer theory, and again, it's a really popular theory that was first proposed back in the 1960s by the anthropologist Dr. Neal. There's a lot of evidence to support it, also a lot of evidence to refute that this is actually correct. But it makes some sense that as hunter-gatherer societies, having very little access to food and having to go long distances to access food, that we should have some way and some genetic ability to be able to store that food in terms of the adipocytes and the deposition of these adipocytes. But again, it's just a theory, and it's one that I wanted to at least bring up for you. And it's been thought that it was maternally inherited at first, mainly because it was thought to have been more beneficial to have the ability to store carbohydrates in these adipocytes for women who were pregnant. Okay, so I think I'm just going to go on for like a couple of more slides. And again, nothing to worry about on these slides here. I've just gone on for a few minutes. Any questions or things that you just want to clarify, confirm whether or not you need to know them or not know them? Anything that's sort of just bubbling at the top of your frontal cortex? Nothing? Is there anything bubbling at all in your frontal cortex? No. Okay. All right. Daydreaming is good. Daydreaming is good. Okay. So I actually had to adjust this down because apparently the McDonald's is becoming slightly healthier. So up until like last year, this number was a little bit higher. So it was like 1,400 calories. And now if you go on to the calorie calculator available at McDonald's Canada, if you order a quarter pounder, exercise fries, large Coke, it's actually down to about 1,220 calories. How many calories do you need typically to survive if you're a male? Average size male, yes, roughly. Sorry? 2,000. About 2,000 calories. So this one meal would pretty much account for most of the calories that you would need over the course of the entire day. And here's where I need you to kind of think as physiologists, and this is the last slide that we'll kind of look at before we go on break. So here's where we're going to start looking at this from a physiological context. And this, again, is going to be really important because some of these will tell me a little bit of how much physiology you remember and what we need to cover in some more detail. So if you're hungry, there are lots of things that actually go into your actions to make you eat. So the physiological aspect, your body needs food. So you have this physiological hunger. Your stomach has been empty, which means that it's going to have these gastric contractions. Some of the cells in your gastric lining will release this molecule known as ghrelin. Maybe having low glucose levels, this ghrelin is sort of your stimulus for you to get moving and to eat. And it's also that ghrelin that is going to allow you to know that you're hungry. But how much food you eat is actually dependent on psychosocial factors. So if you're eating with other people, you're more likely to eat more or to continue eating even though you may no longer be hungry. The time of day is important in terms of like whether or not you're going to eat. Okay, so these are all different psychosocial factors that tell you like how much food you're going to eat beyond the physiological factors. The other thing is like the type of food that you eat is also going to be important. How quickly you eat. So the faster your stomach gets full and it feels full, the quicker you're going to stop eating. Okay, because there are signals that go back through the stretch receptors in your stomach that allow you to kind of know when to stop, and then you feel like you're full and you're satiated. And these are all like really important. Which one is the easiest, do you think, to influence? Which one is sort of the biggest variable? Which one can we kind of fool around with the most? Yes? Yeah, so the psychosocial one is the most challenging one, right? So like how much you eat and for how long is these different factors here are like really important in terms of you being able to control how much you eat. And so we'll come back after break, and then we'll talk a little bit about some of the different aspects of this. So if you can all manage to come back in about 10 minutes, we'll get going at about 4:08 or so, and we'll see how far we get in today's slides. I wonder if this is working. Is this working? Can you hear me? No. Yeah, I feel like it's not. wrong thing. I am tapping now. I should be holding it. Ah. Okay.
Oh, yeah. I just wanted to clarify, these are I was just wondering if we need to know the hunter and gatherer's theory for different, like how much
You have to understand, like, generally what's on this slide.
yes.
A long time ago, we were all food was scarce. People that had the genes to produce carbohydrates as fat.
I didn't take 8 to 8-year-old too, so I don't understand why fat tissue has a lot of it cells.
We're going to talk about
Oh,
immune cells. right. If we're okay, I think we're just going to get going. We'll see how far we get. Probably going to try to finish at around 4:50-ish. We'll see how far we get. There are a couple of really dense slides coming up, so I'll kind of give you the signal when you should probably pay a little bit more attention. So again, if it hasn't been clear, one of the things that we are kind of looking at for metabolic syndrome, it's not just one thing that's going on. It's actually a cascade of things, and they all kind of feed into each other. I've been concentrating on sort of the insulin resistance. And from one of the diagrams that I showed you in the last lecture, this insulin resistance, so hyperglycemia and having hyperinsulinemia. So I went through how you get more glucose in the bloodstream. That's a bad thing. We'll talk about that in some more detail. And then eventually it leads to secreting even more insulin and having hyperinsulin levels. And this is insulin resistance. This leads off into cardiovascular disease. And we'll talk about how having high glucose and high insulin levels cause arteriosclerosis, and how arteriosclerosis in turn can lead to heart problems. Is it polygenetic, or is there something more than just genes that are involved? Is there an environmental component? We're really not sure. So is everyone, the question that I was asking cynically earlier on, is everyone here in this room at risk of developing metabolic syndrome because we're in the era of personalized genomics? So in theory, if I went out and I got genotyped, and it turns out that there are all these published genes that allow me to predict whether or not I'll develop metabolic syndrome, how accurate would that be? We don't know. So that's the bottom line. In 2020, we still don't know all the causes for metabolic syndrome, so I couldn't tell you unless you had a very strong genetic component and it was something that was easily traceable in your genetic family tree. I wouldn't be able to tell you if you were at risk for metabolic syndrome. So not everyone here would develop it, and we couldn't predict it, at least not right now. So in response to sort of metabolic syndrome and the rise of metabolic syndrome, what we're seeing more often is sort of a health consciousness, which is good. I think that the natural consequence of having this really, really strong preponderance and this strong and very, very easily traceable metabolic syndrome and the incidence of it, and it has been going up more and more every year, is actually the response is to think about dieting and other things, being careful around calories. One of the biggest fads that are going on right now, whether or not it will be not just a fad but a trend, and then from a trend into an actual sort of way of life, is fasting. And there are many, many different forms of fasting. So there's extreme forms of dietary restriction, like you're taking like no calories at all. So that's not something that most people would either enjoy. And then the physiological responses that your body have, like you're hungry all the time, you can't really ignore the physiological hunger symptoms that go on. And so abstinence from all food is incredibly difficult for most individuals. And so that's not really something that is done by most individuals. There are different forms of fasting that involve like abstinence from all food, so just like not eating at all versus like keeping your stomach full, the stretch receptors to make it feel like you're eating something, but has no calories, things like water fasting. Again, really, really challenging in and of its own right. Caloric restriction, this again is another way, so just cutting either a quarter of what you would normally take. So instead of 2,000 calories a day for males, just 500 calories per day. Or there are also these other types of fasting, which include fasting mimicking diets, and I'll get into that in some more detail. And if you've been reading things on social media, one of the things that is probably the biggest fad right now is intermittent fasting. And we'll come back and talk about intermittent fasting at the very end of the course. So you fast for a period of time, then you eat regularly as you normally would, and then you fast for a certain number of hours. So intermittent fasting is currently something that many individuals do. All of these things actually affect your inflammatory status as well as induce oxidative damage, and it's not always all that healthy for you, so we'll talk about this as well. In terms of prolonged fasting, So if you're fasting for more than 2 days, this is a form of prolonged fasting. Then you can go back to sort of a normal diet. This is not something that is necessarily all bad for you. So the good part of doing this, and apologies, I don't think you have like the middle bullet point on my slide. So I'll just read those off to you, and you might want to jot this down. So fasting is good. I mean, it's not bad for your body in the short term, and this is why it's done for very short bouts of time, like 1 day, 2 day fasts. So it does decrease blood glucose. So if you have hyperglycemia, fasting does bring those levels down. It also lowers insulin levels, so you don't have hyperinsulinemia. So fasting, if you are in a physiological state that you have like too much blood glucose, too much insulin, fasting helps. IGF, which I haven't talked about yet, insulin-like growth factor 1, IGF-1, it looks a lot like insulin. This is often elevated in metabolic syndrome 2. It's also not something we want to see elevated for too long a period of time. This also goes back down to normal levels if you are fasting. So there are many good effects of fasting, and it's not all bad. And there are many reasons why people fast, religious reasons, but physiologically, these are good reasons to fast. These are hard. So you have that physiological drive to eat, that hunger response that we talked about, ghrelin being that hormone released from an empty stomach that makes you want to eat. And I don't know if you've ever been really hungry. I know we all joke around about being starving students, but I'm guessing that most of you have not gone without food for like a full 48 hours by choice. It's really hard. You get really hungry, you really want to eat, and you feel like you really want to eat. And so fasting is a really difficult thing to do. And that's, again, there are lots of reasons why fasting is important. Fasting is not good, though, for your immune system. It actually does reduce your white blood cell count, so those will go down. It does decrease your liver mass. You want to reduce body mass, that's good, but at the same time, you're also proportionally decreasing your liver mass. And this, again, is a prolonged 2-day, full 48-hour fast. I'm not talking about the types of fasting that different cultures or religions are engaged in. So if you already have an existing malnourishment, of course, fasting is not good for you. So if you have a mineral deficiency or you have some other kind of dietary supplement that you need to take, this is not a good form of fasting to do. Yes, Ananya. Well, if we look at white blood cells sort of generally, and we're talking about the immune system and surveillance, then having a lowered white blood cell count at normal physiological levels and then they decrease after fasting, it's probably not great for your immune system. So if you are someone who's elderly and you already have a reduced white blood cell count, this wouldn't be beneficial. Yeah, so I think, so we'll talk about inflammation in this context in a few minutes. So it's a great question. So if you have like inflammation in general, would reducing white blood cells actually be beneficial? And it's a bit of a trade-off, to be honest. Any other questions, thoughts, or things that are just you're kind of wondering about? Have any of you fasted for like 48 hours, like 2-day fast? It's not easy, and you get very hungry. I've tried it, and I got very hungry, and I don't think that I'd want to do that type of fast again, so it's incredibly challenging. This fasting mimicking diet, though, is another type of fasting that a lot of individuals kind of engage in. It's kind of a modification. Are any of you going to ask me the question, do you need to know any of the data from these slides? No one's going to ask. We're going to wait until like February 4th. Happening on February 4th? Term tests. So do you want to be surprised on the term test? Like, are you the surprise type of class, or would you rather know in advance? Surprise you. Okay, all right. You asked for it. Okay. You want to know now? Yeah, okay, that's what I thought. So you should probably know the details on this slide for prolonged fasting, which again, we're looking at for 48 hours or more, versus the characteristic features of fasting mimicking diets. And this, again, you're reducing the caloric intake for a period of time, generally about 5 days to about a week. So you're not doing this all the time, and you're not eating. You're just reducing your calories for a period of time, and then you're going back to normal eating. And the types of food that you eat in a fasting mimicking diet. So you still take in food daily, but the types of food that you take in where you've already reduced the calorie count, because carbohydrates are rich in calories, you reduce the amount of carbohydrates that you take in. And you reduce the amounts of calories that you take in through proteins, but you take in more calories out of that reduced 40% total in terms of fat. And again, it's not the type of diet that many of you are thinking of, like ketogenic diets that we will eventually talk about later. Ketogenic diets are similar to this, but it's like a normal caloric intake. It's not a reduced calorie intake. So it's a reduction in calorie, but it's thought that supplementing it with high energy source like fat is enough for your body to not feel some of the detriments of this fasting. And there's a hypothesis, and we'll go through this paper slowly over the next little while, that this 4-day fasting mimicking diet, 4 to 5 day fasting mimicking diet, is more beneficial than just a prolonged fasting diet or just straight out fasting. Okay, so we'll see whether or not that hypothesis is correct in the next lecture as well. And you don't need to worry about anything that's over here on the right side of the slide. I haven't really talked about it. Generally speaking, unless I ask you to know something on a diagram, if it's there just for your own information or just to give you additional information. I'll tell you if you need to know something specifically on a slide or not, okay? All right, so I don't know if you are aware of this, but Saccharomyces cerevisiae is actually a model that we use for studying the effects of nutrient fasting. So did you know that you could use yeast to study the effects of fasting? Why would we use yeast? Any ideas? Wild ideas. Yes? Okay, so no hunger cues. Okay, like that idea. It's a good idea. I hadn't thought of that one. Yes? Small, easy to grow, so great physical characteristic of this organism. Great. Anything else? What else would we want to know? So we're in the era of genomics. So are their genes like similar enough to ours? It turns out that they are. So a lot of their genes are actually similar enough to our genes. I know yeast versus humans, you wouldn't think, but there are enough of their genes that are similar enough to ours that we can actually make use of different studies on them. And some of the things that scientists do, they actually engage in these yeast for prolonged fasting. So think a little bit about this and what we just talked about. So you switch these wild-type yeast, so this WT wild-type yeast, between a nutrient-rich medium, so just getting normal nutrients, just like you would eat normally on a day-to-day basis, and you switch that with just water. So instead of exposing yeast to nutrient-rich broth, you switch that broth out, and then you just give them water. And it's like they're fasting. And then you want to know, what is the effect on these yeast? And we need to stress these yeast out. And so one of the things that we use as a stress treatment in yeast, in these Saccharomyces cerevisiae, is hydrogen peroxide. Low levels of hydrogen peroxide applied directly to the yeast after fasting or after not fasting tells us, are they actually more stressed out if they are fasting or they're not fasting? And the simple measurement that we can use is how many of them survive after low levels of hydrogen peroxide exposure. What would your prediction be? Any predictions? So do you think that by fasting, you are blocking the production after exposure to hydrogen peroxide of oxidative radicals, free radicals, and so they're more likely to survive? Or do you think that you actually, by fasting, produce more of them, and so they're more susceptible to dying after? What's your prediction? Is fasting good for yeast or bad for yeast? No predictions. None. None. Okay. Yes. Presuming it would be bad. Okay. Any other predictions? Yes. On the, it's always standardized. Any other predictions? So I'm going to come back to this, but at least in this study, it was shown to be somewhat protective. So fasting here actually lowered or increased the survival of the yeast that had undergone this prolonged fast. So again, a lot of interesting counterintuitive sort of studies. The ones that we probably do most research on, and this again is to also give you one of the sub-themes related to what we look at and what we're interested in. And there's some concepts and some nomenclature that I wanted to bring up. I want to make sure we're all on the same page. So this is also from the same paper, from the prolonged fasting paper. When I mention things like ad libitum, what does that mean? So these mice are given an ad libitum diet. What does that mean? Yes? Right, so they're free to eat as much as they want whenever they want, right? So that's ad libitum, right? So it's like your lives. You can eat whenever you want, as much as you want, as long as you have money in your pockets, right? And then when we talk about this fasting mimicking diet, we'll go back and talk about that later, but I'm hoping some of this makes some sense to you. Are these measures that we would want to look at if we want to see the impact of what fasting does in terms of blood glucose, insulin levels, etc. So does it make sense that they're looking at glucose levels and insulin levels? Sure. So based on what we were talking about earlier, and if fasting is something that will normalize these levels, then we'd want to be measuring glucose and insulin levels in their blood. Does measuring their body weight after fasting make sense? I think that's a no-brainer. Of course, they'd want to know the effects of that. When I mentioned something like a micro CT scan, so think about the CT part of it. What do you think a CT scan is? Have you heard of a CT scan before? I'm sure you all have. If you're not sure, you can just send me your answer telepathically. Go now. Okay, right, computerized tomography. It's like X-ray scans, right? And very similar to what we saw earlier in terms of measuring like different compartments within their body. So we want to do these CT scans like X-ray scans. And then, again, just to think a little bit about this, can you tie any of these organs back to why they would study things like the kidney, heart, and liver? So again, this is fasting, and this is, again, related to metabolic syndrome. Does it make sense that they look at the heart? So let's start with that one. Sure, because if it's related to metabolic syndrome, one of the outcomes if we get too much insulin is that it affects the cardiovascular system. So we'd want to examine the heart. The liver, does that make sense to study the liver? Yep, so the liver is, again, an organ that's affected in both fasting and in metabolic syndrome, so we want to study the liver. And the kidney, did we talk at all about the kidney? Do you remember in metabolic syndrome, one of the measurements that we use, does uric acid ring a bell for any of you? Uric acid, and what was the other part of the uric acid? How good is your long-term memory? Yes. The creatinine, so that gives us a measure of kidney function. And we know that with prolonged metabolic syndrome, that we would be affecting kidney function. So it makes sense to examine the kidney to see if there's damage to the kidney or an improvement to the kidney after this prolonged fasting or the fasting mimicking diet. Any questions on this before we go on? And again, this slide is there just for us to have a common background in terms of what we might be discussing when we look at a paper or when you read a paper. Any questions, things that you're not sure about, anything that you want to confirm? Yes?
What are they looking for in the autopsies?
So typically they would look and do serial sectioning. They would also look at whether or not the heart is enlarged, if the liver is smaller, bigger. They would also look at specific markers for liver damage, etc. So, yeah, basically the animal is sacrificed and all of these organs are kind of prepared for histological examination as well as gross examination. Any other questions? Yes? Well, I'm going to come back to that next lecture. So today I just wanted to introduce this model organisms and then take a look at this. So one of the things that I guess we look at the most often, and I'm guessing that when all of you pick your papers as a group to present in class, in your tutorials, most of you are going to pick either a human study or you're going to pick a study that's related to mice. And I'm guessing that that's because you've either seen mice studies more often or that you're just you think that they're better model organisms. And that's why I wanted to introduce like yeast as a model organism, so think outside the box a little bit. But for the most part, we look at mice because mice are actually really interesting in terms of their pathogenesis. And I'll talk about that in the next slide, not on this one. So as of 2020, right now we have about 300 different genes that are monogenic genes, so one gene, one disease, that have been identified. And we can look at it from a molecular perspective. So this gene either produces a molecule or it has a defective molecule, so it gives us insight into a molecular pathway. And oftentimes, mice are the best way to examine what happens at a systemic level. So if we alter this one gene, how does it alter a molecular pathway, and how does that affect the physiology of the mouse? And we often use that in health and disease. And again, I'm guessing that most of you will pick human or mouse models. No problems in doing that, but I also want you to think that maybe yeast are perfectly valid model systems as well. And here's one of the reasons why, in the context of what we're studying now, why this is really important. So we've been talking about type 2 diabetes, insulin resistance diabetes that leads to cardiovascular diseases, which we call metabolic syndrome. That's what we've been concentrating on. And one of the most interesting things that has resulted from mouse studies and has been verified in human studies, and I'm not sure how much of the history of biology you are familiar with. Back in the 1980s, there was a researcher in Calgary who was the very first to identify, because people were wondering, like, what happens in type 1 diabetes? So often you get diabetes, high blood glucose levels, no insulin production because the beta cells in the pancreas get destroyed. The beta cells produce insulin. There's no insulin, and as a result, no insulin, blood glucose levels just stay really, really high. Many of you will have heard of that. What happens to those pancreatic beta cells? And since the time of Banting and Best, people were trying to figure out what happens. And in 1985, a researcher out of Calgary, of all places, figured out that there is an autoimmune disorder in many forms of type 1 diabetes that leads to the loss of pancreatic beta cells. And that was sort of a earth-shattering discovery that he had made. And about 10% of all cases of type 1 diabetes involves some kind of autoimmune destruction. And it involves some kind of lymphocyte, these immune cells, and these will target the beta cells in the pancreas that normally produce insulin. And this has been known for since at least 1985. So that was well characterized. And you think that science moves really, really quickly, right? So 1985, how many of you were alive? None of you. Well, maybe one of you. I was alive also in 1985. But if you think a little bit about what happened, in the intervening time, people were trying to figure out, okay, autoimmune disorder, check. Pancreatic beta cell loss, check. Insulin loss, also check. All of those things make sense. What is the cell type that actually causes the destruction in this autoimmune disorder? And you have a choice. In adaptive immunity, it's either B or T lymphocytes, right? Unless there's another type that you're aware of. And people were looking to see, like, what cell is it that actually initiates the loss of these different things. And people tried all sorts of approaches. They tried genomic approaches. Since 1985, they've been trying this. And it's only until 2019 that the cell type was identified. And it was identified first in mouse models, and then it was confirmed in human systems. So about 20 different genes in the major histocompatibility complex, or MHC, were examined. They've been implicated. And so we know that in many of these forms of type 1 diabetes, that we have autoantibodies that are there in the bloodstream of people that have type 1 diabetes. They have an autoimmune response against proteins that like insulin, so that would make sense. We also have the presence of autoantibodies against glutamic acid decarboxylase, or GAD. If you have that in your bloodstream, you most likely will have type 1 diabetes, if you have antibodies to this. And if you have autoantibodies to a tyrosine phosphatase known as ICA512, or it's also known as IA2, then you also very, very likely, 99% assuredness that you have type 1 diabetes. So antibodies and autoantibodies, the autoimmune system activation, been known for like well over like 1985, since 1985. I can't do math on the spot. So everyone's been looking for these different cell types, and it turns out that the reason why it was so hard to determine what cell types are actually responsible is that there was a third immune cell type that was sort of hidden. And this third immune cell that was identified in 2019 is known as the X lymphocyte. And this X lymphocyte was also confirmed to be in humans, not just in mouse models, but also in humans. And this X lymphocyte has the cell surface markers that are common to both B lymphocytes and T lymphocytes. It was bizarre. It's been confirmed very, very quickly. And so we now have this new type of immune cell, this X lymphocyte that has both the characteristic features of B lymphocytes as well as T lymphocytes. And if you're wondering how much detail do I need to know about the immune cells and the immune system, just what we're talking about right now. And I'm not going to go through all the different cell surface markers that they help to identify. And this is why mouse models are incredibly important. So type 1 diabetes, big mystery since 1985. The identification as a result of a brand new type of immune cell that has the features of both B lymphocytes and T lymphocytes was remarkable. And that's why no one could find it, because when you're looking for one thing and it's kind of hidden and masked with like the characteristics of another cell type, it would be very challenging to find it. So again, remarkable that a mouse model system has been involved. And these are also known as dual expressor, or DE cells, these X lymphocytes. And these have been shown to be much more abundant in type 1 diabetes. So here's where I'm going to take a little bit of a moment to pause, stop a little bit, to kind of also reflect on a couple of things that are directly related to how you're going to be tested. So oftentimes, and you've seen this sort of on the study guide, I tend to ask questions that are problem-based. So if I give you like a list of different things, and so Bill goes in, he gets his blood drawn, it turns out that he has autoantibodies to X, Y, and Z. What else might you expect to observe? And so autoantibodies, you're thinking right away about type 1 diabetes. And then if you see like in that list a dual expressing or X lymphocyte, then you would also check that. I may never tell you that it's type 1 diabetes, but you'll have to infer all of that information. Okay, so dual expressor cells are an important type, or X lymphocyte is an important type of cell that was derived originally from mouse models that we now think are important in type 1 diabetes. Any questions on what you need to know, things that you just want to confirm, things that you just want to talk about? Anything at all? A good joke that you want to tell me? Always looking for good jokes. No? Nothing. Okay. All right. Okay, so I'm going to ask you a question then. Do we need to memorize everything on this chart? Chart. The favorite things of all profs everywhere. Because you can ask and hide so much information in there. And you can always go back and say, but it's on your slides. So do we need to memorize everything on this chart? No. Okay, so there's nothing that you really need to memorize on this chart. I'm going to tell you about these 2 mice and this 1 rat up here at the top. And when we look at different forms of diabetes, but in particular type 2 diabetes, insulin resistance diabetes, and the reason why we're looking at insulin resistant diabetes is that it's one of the things that's involved in metabolic syndrome, so it leads to cardiovascular, et cetera, is that when we look at mice, and again, we just looked at the value of mice in type 1 diabetes, the elucidation of the X lymphocyte, there were 2 different mice that were found in 1949 and in 1953 at Jackson Laboratories. So if you have done any research here at U of T or anywhere else, you will probably at some point in time ordered mice from Jackson Labs. Do any of you do research using mice or rats? Have you ever heard of Jackson Labs? Omar, have you heard of Jackson Labs?
No, but I was involved in their research.
Okay, you're not making me look very good right now, Omar, but okay, thank you. All right, so Jackson Labs, you're just going to have to trust. They're like a big supplier of mice, and in fact, they're a worldwide supplier of mice. And one of the things that they do is they breed different types of mice. And when they looked back in 1949, they found these really bizarre mice called OB mice, and they had no idea what was going on, but these mice, they ate the same food as every other mouse, but they actually started gaining weight, and they were called obese mice, the OB mice. They also found another similar type of mouse, spontaneously mutated. This other type of mouse, they realized that they had slightly different features, but overall it kind of looked the same, and they called these DB mice. And they're going to be incredibly important mouse models for type 2 diabetes. And then I'll get into the Zucker rats in a little bit later on. But these 2 are ones that I'd like you to make sure that you know are spontaneous mutations that were discovered in mice. And they're incredibly useful as type 2 diabetes models that we're going to be talking about. So that's the only thing I need you to know from this chart. Are we good with that? Are we not good with that? Are we okay with that? I'm going to stop here. Okay. I'm going to assume that we're all okay with that. Okay. So why is this important in our discussion? And I'll try to get through about 3 or 4 more slides, and then we'll try to wrap things up for the day. Do you guys remember PSL 300? Right. How much detail do you remember of PSL 300? Nothing. Okay. It's like that Men in Black thing. So you kind of walk out, you get that little zap thing, you forget everything, right? But I need you to remember a few things. When we eat, that whole drive to eat actually originates in the hypothalamus. This really small group of nuclei in the brain, sitting at the very bottom of the brain, below the thalamus, below the thalamus. This small center in the brain is actually incredibly important for homeostasis. And we use it because mice have a really well-defined hypothalamus. Rats have a really well-defined hypothalamus. And the structure, connections, the neurochemicals are identical to what we find in humans. So not all mouse models are perfect, but they are in terms of the hypothalamus. And again, the hypothalamus controls a lot of basic homeostatic functions, body temperature, but more importantly to our discussion about metabolic syndrome, it involves the feeding and the regulation of appetite. So hunger is the major drive to eat. It's the most hard physiological response to control. And there are other things like psychosocial factors that kind of feed into it. But the hypothalamus drives the eating behavior that begins this whole process. And how is this related to everything that we've been talking about so far? When we look at the adipocytes, and we looked at subcutaneous adipocytes, and we looked at ones that are produced viscerally or stored viscerally within the abdomen, adipocytes are the source of this molecule known as leptin. And leptin is a molecule that is produced by adipocytes, released by adipocytes into the bloodstream, and then work all their way back up to the brain and the hypothalamus, and it suppresses appetite. Okay, so is that clear for everyone? So we have an area in the brain known as the hypothalamus. It is the thing that causes you to want to eat. It's the source of hunger. And then there's this negative feedback molecule known as leptin that is released from adipocytes. And it turns off and suppresses that hunger switch. Are we good so far? And all of this occurs at the level of the hypothalamus. And we know all of this, by the way, through these mouse models. None of this was found in humans. It's been verified in humans, but all of this began in these mice models. And our understanding of leptin came about because of that first OB mouse in Jackson Labs, where one of the technicians, instead of throwing the mouse out or sacrificing the mouse, saying that there's something weird about it, actually took the time to kind of figure out that there's something physiologically unique about the way that it is feeding. And the OB mouse is there on the left, and it is much larger than an appropriately age-matched control mouse that has a normal genotype there on the right. Leptin is produced by the OB gene. That's where the OB comes from. The OB gene produces the transcript for leptin, and then the protein leptin, and the adipocytes then release leptin into the bloodstream. And here's a couple of interesting things about these adipocytes that I need you to be aware of. So adipocytes can undergo division, and this one adipocyte can split off, and it can form these 3 different adipocytes, and they're very, very good at being able to divide. And these adipocytes, in turn, can grow larger as they store more and more of the triglycerides centrally. So wherever you're seeing yellow, after you've eaten a meal, if you have excess calories, they get converted to triglycerides. The triglycerides are then stored within these adipocytes. Once they reach a certain size, they again split off. What do you notice about this pathway? Do you ever lose adipocytes? So as long as you have an appropriate blood supply, you will never lose adipocytes. They're there with you for life. So you can make them smaller. So if you're dieting, you can make them smaller. But you never lose adipocytes as long as you have blood vessels around, and that's adipose tissue. It's not just adipocytes, blood vessels, immune cells, and macrophages. That makes up the adipose tissue. So one of the things that happens in the OB mouse is that the leptin that it produces has a mutation. And so this mutated leptin gets produced, is in the bloodstream, but actually doesn't look enough like leptin to stop the feeding behavior. So the mouse just doesn't know that it's fed enough. Leptin gets released, but it's not enough to stop the feeding behavior, which is why the animal gets bigger. So they have an enhanced appetite. There's no negative feedback control, and they get much, much bigger. It turns out that the second spontaneous mutation that was found 4 years later in 1953 in Jackson Labs actually involves the leptin receptor. So the receptor has a mutation. So in one case, leptin has a mutation, so it doesn't look like leptin. In the DB mouse, the leptin is fine. It's the receptor for leptin in the hypothalamus that is mutated, so it can't respond to leptin. Any questions on that before we go on? Are you starting to zone out a little bit? A little bit, okay. So we'll just go through one more slide. Yes, question? Yes, in fact, they look very, they're not identical, but they're very, very similar. Yeah. Okay, so just again to the next couple of slides, we'll just go through just to make sure that we're all sort of on the same page. So normally, after you've eaten a meal and after you have started to deposit some of the excess calories and these cells are growing in size a little bit, these adipocytes will normally release leptin because the adipocytes carry the OB gene, normal cells. And these adipocytes will start to release leptin into the bloodstream. The more adipocytes you have, the more leptin that gets released. This travels in the bloodstream, and it will then travel up to the hypothalamus. And in the hypothalamus, the leptin will bind to the leptin receptor, and the leptin receptor will then cause the release of melanocortin from the hypothalamus, And this melanocortin, which gets released from the hypothalamus and works its way back through the brain, actually acts as an appetite suppressant. So melanocortin release causes a cessation, stoppage of the feeding behavior. All of this is triggered by leptin. Are we good so far? Can you last for one more slide? Okay. Yes. And Anya, did you have a question before we go on? Nope. Nope. Yeah, so anytime you've eaten a meal and you have like calories left over, then they get stored in these adipocytes. And we're not talking like the adipocytes don't have to double or triple in size. Any storage into that will cause the release of leptin. So anytime you've eaten, you're going to be releasing from your adipocytes, you're going to be releasing leptin. Okay? Any other questions? No? Do you want to play a game where you can tell me how much knowledge you remember from PSL 300, and I'll make it worthwhile without you looking on Google? I kind of doubt. Well, I won't doubt, because you might surprise me again. Without looking on Google and without looking it up, can you tell me the small group of cells within the hypothalamus that actually is responsive to leptin? I'll give you 10 seconds. If you can tell me that, I'll give you one of your multiple choice test questions in advance. And you have to be 100% right. And you have to also say it backwards. Yes, go. Yes. Say it the normal way first and then backwards. Okay, what group of neurons are they? You're right. What group of neurons are they found in? It's called the what nucleus? Not the red. Anyone want to help your friend out? He's on the right track. Starts with P. Yes. Preoptic. Also a good guess? No. No. Should we stop playing? Yes, okay. So we'll learn about this in the next slide, but it's the paraventricular nucleus. Oh, yes. Of course, the paraventricular nucleus. Right, so before we get there, a couple of other things to work in contrast to this, and we'll stop here because a lot of you are kind of zoning out right now. So when we are not eating, what happens is there's a slow, steady buildup, or first there's a lack of leptin, so leptin levels are going down because we're not eating, so leptin is not being released, and these adipocytes are no longer triggering this stoppage of eating. And as a result of this, as blood leptin levels decrease, the negative feedback is being released from the hypothalamus in the paraventricular nucleus of the hypothalamus. And as a result, in order for you to get that hunger signal, is that the hypothalamus will now start to release neuropeptide Y, which will stimulate feeding behavior. So the neuropeptide Y is the sort of opposite, if you want to think of it, of this process. And neuropeptide Y release in the hypothalamus stimulates the hunger response. And normally leptin is suppressing it. When leptin's no longer there, neuropeptide release, peptide Y release is stimulated. So will you have to know about this pathway for your first term test? 100%. So I'm guaranteeing you that you'll see it on both multiple choice as well as your short answer, one-line answer responses. You will get more details of that in your tutorial where you'll practice these and think about that as a group. But you should make sure that you're comfortable with it. I'm hoping that for most of you it's a review from PSL 300, but we're going to go through this and why this pathway is important and why these adipocytes are important at the beginning of the next lecture. Any questions before we wrap things up for the day? No? Do you have any suggestions that we can include since we're all here as a group? Did all of you take a look at the study guide for this week? Do you have any suggestions to improve the study guide, things that you want more of, less of, things that you want to see in the study guide? maybe more questions? Any other suggestions? So more questions, more practice questions. Anything else? Yes. Answers. Do you guys want answers to the questions too? Okay. Post the answers a week after on like the discussion page or something. So that way we have a chance to like time them. Yep. Okay. Fair enough. Okay. Great. Well, I guess I'll see you all next week. Have a great week. Make sure that you go to tutorials. You'll find it really useful and helpful to get you ready for that first term test. And yep, have an excellent weekend as well. Yeah.
Hi.
Yeah.
Just wondering, for these two slides,
Yeah.
are you responsible for like
No.
these
No.
benefits?
No.
Okay. All right. Thanks so much.
No problem. It's a good